Hello, my dear students. Myself S. Devi, Assistant Professor, Department of Artificial Intelligence and Data Science, Rogini College of Engineering and Technology. I am going to teach the subject Operating System and Cloud Basics. Today we are going to discuss about memory allocation. In this section, we are going to see how the memory is allocated for the kernel. First, we will see what is memory allocation. In Linux, uses a virtual memory system where process access memory indirectly through page tables and memory management unit. The memory allocation in Linux can be broadly categorized into physical allocation and virtual memory allocation. Physical allocation in the sense the memory is managed by physical pages, and in the case of memory allocation management, it is handled virtual address space. In Linux, memory is divided into several types: physical memory, swap space, page cache, kernel space, user space. In physical memory, the actual memory is installed on your machine. The swap space is virtual memory on disk used when RAM is exhausted. Page cache, the cache for files that are accessed frequently. The kernel space is the part of the memory that is reserved for the kernel. User space is nothing but the memory allocated for the user process. So usually the kernel function for allocating memory is malloc for small chunks and vmalloc for large since non-continuous blocks. We know that malloc function is used to allocate memory, that is the user space is usually done with the help of malloc function, and mmap and brk function is used for low-level system calls for memory allocation. Kernel memory is treated differently from the user memory, often allocated from free memory pool. The kernel requests memory for structure of various size. Some kernel memory needs to be continuously allocated. For example, in the case of IO management, it needs continuous memory allocation. Different types in allocating memory. The first one is slab allocated. The slab is a memory management mechanism used in Linux kernel, and it is also used in Unix to efficiently allocate memory for the kernel object. It is mainly designed to reduce memory fragmentation. It reduces the overhead associated in repeated allocation and deallocation. It improves the performance by minimizing the overhead of repeated allocation and deallocation object. See what is slab first. Slab is one or more physical continuous pages. Cache consists of one or more slabs. Single cache for each unique kernel data structure. Each cache filled with object instantaneous of the data structure. When the cache is created, it is marked as free. When structure stores objects marked as unused. If slab is full of objects, used objects, next objects allocated from the empty slab. If no empty slab, new slab is allocated. Its main benefit is that it includes no fragmentation, fast memory request satisfaction. The main concept of this to allocate memory for the kernel object. This is the diagram for the slab allocation. As I told that the slab is a continuous memory region. Cache is a collection of slabs, each containing object of same type. Here, instead of destroying object, they are marked as free. That is, instead of deallocating the object, it is marked as free. So the working mechanism is, the first one is cache creation. A cache is created for each type, and cache contains slabs and slabs contains multiple objects. The slab allocation is the each slab is divided into slots and each slot is pre-allocated to hold the instance of the object. So in the case if the none are available, it allocates a new slab and add it to the cache. The case of deallocation, when an object is no longer needed, its slot is marked as free. Instead of destroying it, it is marked as free. Cache management. The slab allocation keeps track of which slabs are full, which slab is empty, and which slab is partially full. So there are three states, that is full, empty and partial. Empty means all objects are freed, full means all objects are in use, and partial means some objects are used and some objects are free. That is mixed of free and used. So slab allocator type in Linux is slab, slub, slob. So there are three things to consider. The slab is original implemented supported object coloring cache alignment. SLUB is simple and fast replacement of slab. It is default in a kernel. SLOB simplified version for embedded system with small memory footprints. As I told you before, the advantage of the slab is it reduces fragmentation, it improves performance, reduces overhead, efficient memory utilization. And the disadvantage is fixed size object allocation, waste memory if object size does not align well, complexity in management slab states. And the second type is PROC, PROS. In Linux, the prox file systems, especially the prox memory info file, provides a way to view memory usage information for the system, including details about the physical memory, swap space, and various memory caching. It doesn't directly represent how memory is allocated for the process. In Linux, the virtual interface that provides real-time access to the kernel and process information, including memory allocation details. It is a pseudocode file system that exists in the memory and does not occupy disk space. It exposes kernel and process information to user space. Each process has its own directory, that is pros. Within that, it has another that is process ID. It contains the detailed information about the process information, kernel information, dynamic data, interferences for utility communication. The process information, in the sense it contains directory named after process ID, each holding files that reveals details about the specific process, such as its state, memory usage, open files, and more. The kernel information, in the sense, is provide access to various kernel parameters, hardware information, and system-wide statistics. Dynamic data means the information is not stored on disk. It's dynamic, generated by the kernel as needed. This means it reflects the current state of the system. Interface for utilities. Many system utilities like PS, TOP, LSMOD rely on pros to gather information about the process and the system. And the last one is communication. It acts as a bridge between the kernel and the users. It is essence is a powerful tool for monitoring and managing a running system, providing a convenient way to access and interact with the kernel level data through a familiar file system interface. The key entries for memory management using process. It provides information about the system-wide memory usage, containing fields like memory, total memory, free memory, buffer, caches, total swap space, total free swap space, etc. And the next one is it will give the information about the status, showing the memory usage of a specific process, that is VM size, resident set size, VM data, code, and stack information. And the third one is it lists the memory mapping of a process. It shows how memory regions are laid out, including stack, heap, shared libraries, executable code. It also provides information about the memory usage in terms of pages, that is the size of the page, resident set size, shared pages. And the third type is top. In Linux memory management system, the top command in Linux can provide an overview of the memory usage, but it doesn't shows memory allocation in a very detail of a specific way. The first one is top for memory allocation. This shows the system's summary information, including memory usage, that is the memory in the sense total memory used, that is the total amount of RAM available, the memory that is currently used by the process, and the memory that is free, the memory that is not being used by the process, and the memory used by the kernel buffer and page cache, and the memory available for starting new process without swapping. And the command is stop. This will display all these information such as total, free, buffer, cache available, etc. And the next one is the command used is HTOP. It provides the interactive color-coded display of system resources, including memory allocation, which is more user-friendly than top. You can install HTOP if it is not already available. So the command is HTOP. It will give the detailed information about the real-time overview of the system memory, process, CPU usage with a graphical representation of memory usage. Using free memory is free, used total and shared buffer caches. That is also similar to that only. That is used memory, free memory, total memory, swap memory. Memory info will also provide the same information like details breakdown of memory allocation, including free, used cache, buffer, swapped cache, etc. The fourth one is vmstat. Command is powerful tool for monitoring system performance, especially memory usage. It provides a snapshot of the various system metrics, including memory, process, paging blocks, input, IO, input output, and CPU activity. The memory fields are SWPD. It provides the amount of virtual memory used, and next is free, the amount of ideal memory available. Next is BUFF, memory used as buffer by the kernel. And the fourth one is cache. It provides the information about the file system cache. SI, which will provide the information about this memory swapped in from disk per seconds, that is per KB per seconds. SO is it provides the information of swap per second. And we have various CPU fields, US, which provides time spent in user mode. SV is nothing but it spends in system kernel mode. ID is the ideal time. W is the waiting time for IO. ST is the stolen from virtual memory by hyperversion. The example one, that is VM stat 5 space 3, it gives the information that the command print system stats every 5 seconds for the total of 3 updates, useful for observing memory behavior over time. The second one is VM stat space 1 space 5, it will display the output every second for 5 times. Advanced option is VM stat space hyphen s, displays the detailed memory statistics and even counters. VMstat minus hyphen a shows the active and inactive memory instead of buffering cache. VMstat space minus m displays the slab allocator states, that is kernel memory usage. So this is all about the allocating memory to the kernel. So we will see the next topic in the next session. Thank you.